All right, so hello everyone. My name is Felix Zhu. Today I have a presentation on the applications of shape memory alloys in aircraft flight control surfaces. This is a project I've been working on for quite a while, as with other SYP students. But yeah, so I'll get started. So behind me is an image of the 1903 Wright Flyer. It was the first ever successful powered aircraft to take flight. The Wright brothers, it was actually Orville Wright who took it to the skies on December 17th off the Kill Devil Hills in North Carolina. It flew 120 feet in its first flight over the course of 12 seconds, which amounts to 7 miles an hour. 7 miles an hour is well below human running speed, but you can still crash at 7 miles an hour. So how do you maintain control over an aircraft that is flying, even if it is flying at 7 miles an hour? The Wright brothers' answer was the technique called wing warping, where you flex the wings. I'll get back to that very quickly after I show you the traditional or the modern flight control surfaces that are currently favored. So this shows the flight control surfaces of an aircraft. The ones I was really interested in were the ailerons, which you see in the top right. They are essentially a separate solid fixed hinged panel that the pilot actuates when he is flying to roll the aircraft. That means turning it laterally. By moving it up or down, you affect the pressure balance on each side of the wing, and you thereby push one side of the wing up and the other side down, and that rolls the aircraft. Wing warping, you can see here the Wright brothers' original patent for the technique that they used. They actually flex the entire wing surface itself. So you have a single wing that is very flexible, and then by manipulation of the hand controls, you actually move the entire wing structure rather than just the separate panel. Now this theoretically is more efficient than the modern system because there's no gaps between separate panels for airflow to pass through, thereby reducing lift. And there's also no in modern aircraft at least, there would be no separate ridges or whatever to actually interrupt the airflow and increase turbulence in the wing. However, there are certain drawbacks to this system in that this modern sort of layout, it's very stable. You can have an extremely rigid wing and not worry about it flopping around, violent oscillations and such. Mechanically speaking, from an engineering standpoint, it's a lot simpler to design such a wing rather than having a wing that's highly flexible. And as such, wing warping was abandoned pretty early on in aircraft history. I think like 1917, they already began sort of phasing them out. And because at high speeds, you had instability from oscillations. You had involuntary rolls where when you're flying, maybe the wind picked up a little bit, the entire wing would just start bending around and your plane would just flip over. And there was also a tab effect where by manipulating the hand controls, the entire wing would flex in a different way, and then you would just flip over in the opposite direction that you wanted to pretty violently. So it was abandoned. However, with the advent of new technologies, mainly with computers and the sensors and whatnot, they've actually begun re-examining this, especially at NASA, where they're looking to what's called wing morphing, where it differs in that they use computers to control the attitude of the wing, and they use computers to constantly monitor how the wing is flexing. So this is an image of the X-53. It's a NASA modified F/A-18. This was actually one of the first F/A-18s made, but they acquired in 1999 to test their new wing called the active aeroelastic wing. This uses essentially the same basic flight controls as a modern aircraft does, except they use more of them spread out along the wing, but they're a lot smaller. So the way this works is they have a very flexible wing, and they actually use the flaps along with the ailerons and whatnot. They actually use those to affect the amount of force on each side of the wing rather than simply just changing the pressure on each side. They actually use that pressure rather than to generate lift to actually flex the entire wing. So For example, you'll have, at low speeds, you'll be using this as a normal system. The computer will simply, it'll make minute adjustments and then it'll fly like a normal aircraft. However, once you start getting into high strains, it'll actually act in the opposite direction to induce that tab effect, which was so detrimental in early aircraft, but in the opposite direction, so the direction that you actually want to go, which means that it increases the roll performance of the aircraft, as well as actually increasing the efficiency because it uses wing warping, and so there's reduced air load on the wing. So the test results of the X-53 show that the aircraft was lighter. There were lower strains on the aircraft. There was reduced drag. And in high strain maneuvers, so maneuvers where you're pulling a lot of G's or whatever, there was reduced air load, which means that there were fewer aerodynamic forces acting on the wing. It used those forces more efficiently. And it also enabled for a higher aspect ratio wing. Aspect ratio being the ratio from the wing tip to the wing root and the wing chord line, which is from the leading edge of the wing to the trailing edge. That ratio is important because with an increased aspect ratio, you actually get an increase in efficiency because reduced wingtip vortices, because the smaller distance that the air has to travel in order to actually generate the same amount of lift. So there are alternatives to this NASA technology of active aeroelastic wing. I examined shape memory alloys, but there's another alternative, which is piezoelectric chips. Piezoelectric chips are essentially just small chips that once you apply an electric current to them, they bend in a certain direction. The piezoelectric chips are cheap and they're easy to use and they can double as sensors. However, they don't put through as much force as the potentials, or as shape memory alloys have the potential of outputting. And they also can take fewer strains. So if you bend them too far, they might break. Shape memory alloys, on the other hand, are more expensive. However, they are highly flexible and they can take a lot of force and they can output a lot of force. Now I'm going to explain how shape memory alloys exactly work. The one which I examined was Nitinol, which is a nickel-titanium alloy, roughly 50-50. It depends on the grade and on what temperatures you want the phase transitions to be at. Ni stands for nickel, Ti stands for titanium, and NOL stands for Naval Ordnance Laboratory, where it was first discovered. So nitinol's functioning depends on two things. It has two properties which can describe its functioning. One is thermal hysteresis, which is it means that it has dependence on its both current and past states based on temperature. And I'll get back to that after I explain Martin-Sittig transformation, which is the other aspect of its functioning. So there's two crystal structures within nitinol. It has an austenite, which is also known as the parent structure. It's a cubic crystal lattice, and a martensite phase, which is at lower temperatures. It's called the daughter phase, and it's a more complex monoclinic structure that you can see there. So the transition between the austenite and martensite phases is based on temperature, so the thermal hysteresis that I was talking about earlier. And so in the martensite phase, you can bend nitinol however you want. It won't sort of push back. You can form it to whatever shape you want. However, once you put it to the austenite phase, it actually snaps to a certain rigid structure. So, and that's where its applications come from, where you can actually put, say, an electrical current through it, which is what I used. And it will increase the heat, and then it will actually go to a preset shape, which the setting of it you can set yourself by exceeding yet another sort of threshold temperature. The really important bit with shape memory alloys is not that it can remember a past shape and go to it, but the fact is that it can actually exert a pressure while it's reverting to its past state. So when you heat it up, in general, nitinol will exert around 35,000 psi of pressure. But in certain lab tests, they've actually, a lot of times actually, they've exceeded 100,000 psi of pressure that they can exert with a strand of nitinol. So the applications for having a larger sheet of nitinol, the amount of pressure the amount of force you can actually exert with just that are actually they're quite impressive. Nitinol has actually begun entering sort of modern our economy or whatever, the market. There are lots of uses that they've actually begun using them in glasses. Some of you might have seen glasses that are bendable. You can twist them whatever way. There are advertisements for them. Those are actually made out of nitinol, where the austenite phase is actually at room temperature, so it differs in mind that you actually normally don't see the martensite phase where you can bend it around freely. It's at room temperature, so when you twist it around, the moment you let go, it springs back to that preset shape. They use them in orthodontic braces, where they actually, your body heat is actually what sort of forces the teeth into the correct position, rather than using like elastics or whatever, that kind of thing. It doesn't require constant readjustment because you can just set it to a shape and it'll hold in your mouth and it'll slowly push it back through a gradual application of force. They use them in medical stents, where they put them into your arteries to stop a blood clot, for example, from occurring or whatever, those kinds of things. And they use them in medical tools where you stick them into the body and it'll cut on its own very cleanly. And they use them in heat engines, where they actually take advantage of a temperature difference, where it'll flex to a certain position under a higher temperature, and then the moment you pass it through to the colder area, it'll unflex and use the momentum of that flexing to actually generate energy, or generate mechanical energy from the heat transfer. And what I was specifically interested in was the artificial muscle, where they actually use it as what they call a shape memory actuator. So here you can see two pictures. There's the meshworm, which is a MIT robot that is almost entirely made out of fabrics and nitinol. So you essentially have a fabric around which is woven this spring of nitinol, and by applying current through the nitinol, they contract a series of those springs in a very organized fashion, and through that they can move it along the ground like an earthworm does, just contracting and then going forward. And the meshworm is actually very resilient. They've hammered it and they've stepped on it and it still doesn't break, and they show this in their it's like part of their campaign to get awareness out about this. And then there's also the Navy lobster robot, which they've developed a robot which uses legs. It walks along the seafloor, and then if it comes across an unexploded underwater mine, it detonates itself and it takes out the mine without damaging other people. But yeah, so they use nitinol as the basis of the actuation for the legs in that robot. Now, how the actuation actually occurs in most of these cases, including mine, is through Joule heating or ohmic heating. It's where you apply a current through it, through the nitinol, and the increase in heat is proportional to the current squared multiplied by the resistance. So what this means is in nitinol, if you apply current through it, if you have a higher voltage, the current will increase, and so the higher voltage will increase the temperature more, and so yeah, so it actually this was important. The fact that it's a function of current squared multiplied by resistance is actually important in using nitinol as an actuator, because with a decrease in current, so through, for example, by increasing resistance, so for example having a longer length of wire, you actually decrease current, and because of the fact that so power is a function of currents and current and voltage. Sorry, that's I'm trying to remember the function right now. Huh? No, it's all right. Whatever. So okay. So the important thing is that when you have a set amount of power in a system, if you increase the resistance, the current will actually decrease. So those are directly or inversely proportional to each other. So because of this, when you increase the current, resistance decreases, but the amount of heat generated actually decreases by a factor of the resistance squared. So the heat decrease is actually significantly increased with a small amount of decrease in resistance. So in short, so the decrease in, so in short, if you want to have a effective increase in heat, you want to have a shorter, thinner strand of nitinol rather than a long one. So that puts a large sort of power requirement on your designs or whatever if you're actually trying to effect a change on a larger amount of nitinol, which means that there's sort of you sort of hit a weight restriction with your RC plane or such a thing as I built. Now back to the wing morphing. So the advantages of nitinol in wing morphing are that it's flexible, so it doesn't actually it doesn't counteract the flexibility that you actually want from a wing morphing system, and it exerts a very significant amount of pressure. So the amount of force is not an issue because it can easily overcome the force requirements, and it keeps the same benefits obviously as your traditional wing morphing system, where you have increased efficiency, no panel gaps, no no extra sources of turbulence, and you have less drag when you're actually using it, as I went over with the active aeroelastic wing that NASA tested. Wait, is this? Okay, yeah, it is. Now, there's a reason why I put the potential areas where it could come short, because so the slower actuation of nitinol, the increase in heat, it means, well, nitinol itself, it has sort of a limit on the number of times you can actually move the nitinol back and forth, the amount of times that you can cool it and heat it and cool it and heat it per second. I believe they've only tested it to about 6 times per second, which is still fast, but it's not quite as fast as piezoelectric chips can put out, which is the alternative sort of technology. Those can put out several thousand actuations per second, which, you know, it's an advantage when you're trying to have a control surface for an aircraft, where you get sensor input at several thousand times per second, so the adjustments have to be very fast. And there's a reason why I put the effective in small scales there, even though it should be a potential benefit. So I tested it to be effective in small scale in the project which I built, but however, the joule heating, the weight restriction that puts on an airframe, it means that so with a larger sort of aircraft, because of the cube square law which I put there, actually wait, let me just step back for a second and explain the cube square law. So the cube square law, this is straight from Wikipedia, the definition. When an object undergoes a proportional increase in size, its new volume is proportional to the cube of the multiplier, and its new surface area is proportional to the square of the multiplier. So this is important because if you have an RC plane, as I built, you scale it up twice, the actual volume of it, and therefore its inertia, actually increases by the cube, so by a factor of 8 rather than just the length of factor of 2. Now this means that with more inertia, it requires more force to maneuver the aircraft, and more force requires a larger strand of nitinol, and larger strand of nitinol requires a yet increased amount of voltage to actually affect the temperature change that you want. So what this means is, rather than having aircraft that's twice as large and then just having twice as much voltage going to the wires, you need it 16, 32 times greater just to actually affect the change that you want. So on small scales, it's quite practical to use nitinol. You can do it quite easily, but on a large scale, you need a lot more funding. You need high energy density in your batteries and whatnot, just to get the weight, or just to get under the sort of weight restrictions that an aircraft has, because a heavier aircraft means a less efficient one. So you sort of counteract that, the effectiveness that you're talking about. So this sort of begs the question of what are the next uses of nitinol? If there are better alternatives in the use of ailerons, what can you use nitinol for rather than using wing warping just to change the roll? And NASA actually put together an animation. I have a few screenshots of it here, I guess. So this is the NASA sort of Eagle sort of concept aircraft. So nitinol obviously has limitations for wing warping. However, it does have a greater level of flexibility in terms of the amounts of shapes that you can have than piezoelectric chips. Rather than just affecting a bend in one direction, you can have, for example, a straight wire of nitinol, and just a single increase in heat would lead to a very complex pattern that you can create. And so with computer control and with nitinol, you can actually create an aircraft with a completely with an airframe that's complete. You can change the shape of at will. You can increase the lift or change the roll or whatever, not simply by having extra flaps or extra slats in the front to sort of maneuver air around more effectively at low speeds or whatever, but you can actually change the entire shape of the aircraft. So you can have an aircraft that's more efficient at high speeds and an aircraft that's more efficient at low speeds, generates more lift, has straighter wings, or less drag with a swept wing design. This actually means that at each, as you're taking off, you can have the most efficient layout for an aircraft that's taking off. As you're cruising, you can have an aircraft that cruises at that has a shape that is specifically tuned for that particular speed at which you're cruising at. So you end up with an aircraft that has a massive increase in efficiency. And so in this specific regard, nitinol is actually a lot better suited than piezoelectric chips, and the other technology of active aeroelastic wing has no effect on this, purely by the fact that it's based on a very traditional kind of layout. So yeah, that concludes my my presentation on the potential uses of nitinol. Thank you very much.
We have time for Q&A.
Yeah. Yeah.
But, you said that you actually.
Yeah. So. I actually built a RC plane. This presentation was simply on the potential uses of it, but I actually built as my primary research an RC plane that actually has it can use nitinol as its actual wing warping sort of system. I actually built it to have a single fuselage around which you can stick in either a traditional set of RC plane wings or a set of wings which I built, which actually uses nitinol. And I actually have some in-flight video. Do you guys want to watch that? It's kind of fun. Let me see if I can get to it. I'll have to download it, but here, this one. This is a good video. All of those are actually shots. Not all of them are good. Some of them are me crashing. Okay. Let's see. Some technical issues. Wait, whoops, wrong button. Oh, where is it? Is there another program for opening this stuff?
Yeah, VLC.
Yeah, VLC should, yep. So I was actually flying this around north. This was the day before I crashed it, actually. I mounted my cell phone in it, so I wasn't being too ambitious with the flying in case the cell phone fell out. But yeah. It took me a few tries to be able to actually fly the plane. The first few times, I crashed it like 5 times in a row, and the wings were falling out and stuff. But
How big is it?
it has a 1.5 meter wingspan, so it's actually pretty large, like this big kind of. So you can actually see like later on in the video, you can see pretty far. Yeah, like Boston right over there. But yeah, it's a lot of fun to fly.
How high up is that?
I have no idea. I would need like a barometer to be able to tell that. But yeah. So the actual electronics took a while to figure out in regards to how to control the aircraft. I actually had to buy an electronic speed controller for a DC motor. So in your traditional or your modern RC plane, they use brushless motors, which run on AC current or alternating current. So that doesn't work as well in regards to joule heating. So I actually had to get a electronic speed controller for a DC motor, for a remote control truck, to actually to be able to vary the amount of the amount of voltage that's actually going to each wire. And the electronic speed controller that I actually had was it had both reverse and forward. So that I actually got that specifically so that I could have 2 sets of Nitinol, one for rolling to the right, one for rolling to the left. And then I would put a positive voltage for the one rolling to the right, and I'd have diodes to change. So if it went to the right, I would have it go through positive voltage, so it would only go through one of the diodes. And then I would have another diode for if I put it voltage the other direction. But yeah.
How did you set your Nitinol? So you use Nitinol?
Yeah, so Nitinol, the way you set it is by pushing it past a certain threshold temperature. So I actually got a heat gun, yeah. So I used a heat gun to get it past, I think it was around like 500 degrees Celsius. And I held that for a few minutes, and then it's set to shape. Yeah.
So since you can only hold one shape in the Nitinol,
Yeah.
is it really viable to, when you're in flight, are you going to use the Nitinol to?
Yeah, so the banking here, so the rolling around,
Yeah.
that's actually through the Nitinol.
Okay.
So I actually had 2 separate groups of Nitinol. One of the groups was for pushing the aileron, or not the aileron, but like the wing up, and then the other group was counter to that. So I would put a voltage through that one, heat up another set of wires to push it down.
Okay.
An interesting thing about Nitinol, I couldn't really use it in this application because, so yeah, that's kind of getting crazy now. The wind started picking up. But yeah, here I was trying to land it, but the wind was kind of blocking my landings. But yeah, an interesting thing about Nitinol is you can actually, they refer to it as training the Nitinol, where when you cool it, you can actually set it to another preset shape when you cool it. It's very, it's sort of a complex process, but it's actually, I couldn't use that for this particular application. I couldn't have it be so like I had this sheet of Nitinol and I'd heat it up to have one direction, cool it down for the other direction, because with heating up, it's relatively easy. You just put a current through it. But when you're trying to cool down something, you'd have to rely on the ambient air temperature in this particular situation where you have such a restricted weight requirement. So cooling it down was kind of it wasn't a possibility in my application. But yeah, and there's a landing.
So one more question.
Yep. Oh,
If
whoops.
I hold a paper clip
Yep.
and I move it back and forth, we know that it's going to break at some point
Yeah.
because of work hardening.
Yeah.
Is that going to happen?
Nitinol, one of its other properties, which I didn't go into here, was it has what's called super elasticity, and so it's highly flexible, and you can actually bend it around to huge strains, and then it actually won't really have much of a negative impact on the Nitinol. So it's a highly flexible material. So it probably does have sort of a shelf life, but in tests they haven't yet gotten to that. Yeah.
Have you ever looked into carbon fiber composites as well?
Yeah. So actually, I used them in the plane. So for example, with yeah, exactly, because it's lightweight, yeah. So yeah, I use that as like, for example, the central spar of the wings, so the wings wouldn't oscillate too much, like up and down while I was flying at high speeds. The spar was made out of carbon fiber and that kind of thing.
Do you know
But
if they use them in like the bigger aircraft? Like
yeah, they do.
Mix it in with them?
I'm not sure if they've begun applying Nitinol to large-scale aircraft yet. There's still a lot of research going around that. Yeah, exactly. I've seen papers on applying them in structures called chevrons in the engines of aircraft. Chevrons are they're essentially like, if you look at an aircraft, sometimes the edge will look like it's serrated, and those are actually chevrons. And chevrons are designed to reduce the sound of an aircraft as it's flying. But yeah, they've looked into shape memory chevrons to be able to manipulate the amount of sound that an aircraft engine is producing. Yeah. Any other questions? All right. Thank you very much.